know if Natasha's going to be on, but Mark from University of Arizona Lunar and Planetary Laboratory is going to take you through some background and introduction to what you'll be doing tomorrow. So Mark, are you ready to share your screen?
I'm ready to go. All right, does that work?
Looks good.
Okay, well, hello everyone, and welcome to the second hands-on session topic. Natasha, Batalha, and I will be leading this, and we've heard so much this morning about trying to understand the directly imaged planets and all of the challenges in modeling them. What we're going to motivate is the tools that originally I developed and that Natasha has converted into Python and made much easier and publicly available so that you can produce your own spectra of these planets and start to understand, how can we characterize the objects once they've been found. So I am the brand new director of the Department of Planetary Sciences in the Lunar and Planetary Lab at the University of Arizona. And the topic that I will do this morning is just to motivate a little bit about what the hands-on session is going to be doing, and then Natasha will walk you through what the actual procedures are. So I'll start with this very nice table that Carl showed on Monday morning. I know several people that stole it with a screenshot, and it tells you for the young planets in particular, ages under 300 million years, how many have been found by the different discovery methods. And direct imaging really excels at discovering these young, warm, giant planets. Whereas transit timing or transit methods or radial velocity is much harder because the stars are young and variable, and it's difficult to do these methods.
Mark, I still see your title slide.
Oh, it's not advancing?
We still see your title slide.
Oh boy.
Okay, now we see it.
Okay, I'll just leave it. I'll leave it here then. So this is the various methods, and there's the which Christoph was just mentioning, the HR 8799 planets down at the bottom. So once we have these discoveries, what are the planetary properties that we can infer from the spectra, the mass, the effective temperature, the metallicity, formation mechanisms, and so on. So sort of the first step is the characterization from luminosity. So just measure the luminosity of these planets, measure their spectral energy distribution by measuring the flux at as many different wavelengths as possible, and then comparing that to model cooling tracks that are computed at the age of the star. And of course, as we heard on Monday, even getting the age of the star itself is difficult. But if we take the limits from the comparisons of the star to the stellar models, that gives us an age for the planets. And the little snippet of a table just shows a planetary evolution model, which for a given age and a given planet mass predicts a luminosity, effective temperature, and all the things you want to see. But of course, the evolution of the planet through time depends on how it formed. And the traditionally, pre-20 years ago, the models for all of these planets were computed from what we now call hot stars. So hot initial conditions that the planet almost formed in isolation, collapsed down from the nebula. And these planets are shown by the dotted curves in these evolution models along the right-hand side from these hot initial conditions. But with core accretion, the core accretion models predict that during the formation of the planet, much of the mass comes in through the nebula, through an accretion disk. A lot of luminosity is lost to an accretion shock, which is shown on the evolution panel on the left. Here's luminosity versus time. And you see those spikes in these models around 2.5 million years or so, where the planets are bright and they've lost a lot of their internal energy. And thus the core accretion planets in this particular case are born smaller, cooler, and fainter. So smaller radii, cooler effective temperatures, and lower luminosities. And it turns out exactly how the model works and exactly what assumptions you make affect this. And you can have these cool models through a whole range of possibilities in between sort of the limit case that's shown here in the figures on the right and with different assumptions, you can get closer back to the hot start models, the dotted lines. It's worth noting, because I'm going to come back to this later, that the smallest planet radii at these young ages is about 1 to 1.1, 1.2 Jupiter radii. They never get any smaller than that for solar composition giant planets. And so here's an example of looking at 51 Eri B. This figure is from Rajan et al. In 2017. And again, we see the hot start models and the dotted lines, the cold start models in solid. And there's 51 Eri B at an age of about 25 million years or so. And you can see that the luminosity is low enough, at the age is young enough, that this planet could have formed either through core accretion, through these cold start models, or through a hot start case coming down from the top left. And so this is sort of the first step in understanding, okay, what are the possible formation mechanisms? Whereas the companions up at the top, like the brown dwarf companion to the brown dwarf 2 mass 1207, really had to have started as a hot start. It really could not have started as a cold start. So we can do the luminosity, but what we'd really like to do is go to the next step, which is characterization from spectra. And the spectra is nice because now you're starting to learn something about the composition of the atmosphere, and from interpretation of the spectra in comparison to models, you can get information on the gravity, whether there's clouds, and so on. And the top right figure is from Oppenheimer et al. In 1995, the discovery of Gliese 229b, and there in H band around 1.7 microns, there's a bite out of the spectrum, which is similar to what is seen in Jupiter. And it turns out that's from methane. And you only get methane in a cold atmosphere. And so this is an example, kind of a canonical example of using the molecules that are present to tell you something about the temperature. The bottom panel shows the ratio of methane to carbon monoxide at a grayscale or a color scale. And as you can see, you only get appreciable methane to the left of about 1,000 degrees in these atmospheres. And so that's an example of a molecule being an indicator to tell you about what's going on. Today, for the hands-on sessions, we're going to give you temperature pressure models for the atmospheres of the directly imaged planets. And so we're sort of saying, accept these as being truth. And we're using, no coincidence, my own recent models from Marley et al. 2021. But you really can use any temperature pressure profile that you might have and give that to Picasso, and then Picasso will compute a spectrum. So once you have a set of models in hand and you go off and look at your planet, again, looking at 51 Eri B, you can then start to say, okay, now here's the 51 Eri B on the top left. This also has the methane cutout at 1.7. You can see the absorption of methane and the absorption of water around 1.4, and then start to tease out what's in the atmosphere, what the temperature is. And if you have a grid of models like the Sonora models, you can sweep through all those models, compute spectra for each of the models, and compare those spectra to the observations. And so, again, this is just an example. Back in 2017, we did that and found that the best fitting model were at 900 Kelvin and log G of 3.5. In this panel, cloudless, so no clouds, and everything looks pretty good. And you say, okay, it's not a perfect fit, but it's a decent reproduction of the data. But then you look at the implied radius from the gravity and fitting to the spectrum. And in this case, it comes out at about half a Jupiter radius. And I'll remind you from the evolution is that you never get below 1. So then this is not a satisfying fit after all, because while maybe we can fit the spectra, we have to also remember the evolution and the evolution through time. And so those two things seem to be in tension, which means we don't truly understand. And so it's important to remember as we do spectra fitting of data, you can't just think of the spectra by themselves. It's the whole cohesive whole that we have to think about. So again, doing these kinds of fits, sweeping through all model parameters requires model atmosphere grids. And here's, again, just some sample ones from what we're calling the Sonora Bobcat series of models. And these are all showing the run of pressure and temperature. If you were to drop an atmosphere probe down into the atmosphere of these planets or brown dwarfs, this is the temperature and pressure you would record. The whole process by how these radiative convective equilibrium models are computed is a whole other story. And again, we're not going to go into that this morning, but rather just giving them to you as a database to refer to. We think they're pretty good, but they're certainly not a perfect description of reality. And this is something that the modelers are constantly working to improve. And an important point is that we are ignoring clouds for the exercise this morning, again, just for simplicity. Once we have these models, we can look at the composition space and see for these are different models here in different colored lines, seeing where you are in pressure, temperature space, seeing what species are predicted. And then the dashed lines here show clouds that form. So for example, the hot curve on the right crosses the condensation curve for iron, and you would predict that there would be an iron cloud there. More towards the middle of the panel, we see we're crossing the KCl condensation curve. So these particular models, you would predict clouds of potassium chloride to form. And then finally, the very coldest models are passing the water condensation curve. And so what you predict then really is kind of a stacked layer, depending on where you are in this figure, a stacked layer of clouds. This little panel is from Katrina Lauder's showing notional cloud profile for the atmosphere of Jupiter, where you have iron clouds deep, the potassium, sodium clouds in the middle, and then water clouds at the top. So again, everything we're going to do today ignores clouds, but I have to, just remind you, if you were trying to compare these data to the real thing, a lot of the exoplanets have clouds, which makes it more difficult to model. And the way to think about, okay, if I have something that I use Picasso for and predict a model spectrum, how might it be different if there were clouds? Now, Picasso has a way you can actually specify the properties of the cloud and it will do it properly. But sort of to give you a little bit of intuition, most of the flux, or the flux comes out through low opacity regions, say regions of the water opacity where there's the opacity is low, and that means you can see deep in the atmosphere where it's hotter. And so if there's no clouds, this is an animation, so it's, let me take out my cloud here. So in the case with no clouds, the flux from the deep atmosphere is bright, and so it gives you a spectrum that looks like the top panel, say where the minimum of water band, the atmosphere is, you see deep, a lot of flux from deep in the atmosphere. So you're a peak in the spectrum, and then to either side, you're seeing higher up and where it's cooler and you're not emitting as much. But if we put a cloud in, it changes that because now the cloud has sealed off the deep atmosphere. You don't see it. You're not getting flux from deep in the atmosphere. And so we lose the peak. And then also it warms up the rest of the atmosphere above the cloud and it brings up the sides. And so the bottom line is just that the clouds tend to reduce the peak to valley dynamic range you see in the spectra. And in general, clouds redden the near infrared colors. Here's an example from a brown dwarf, these 0255. Details don't matter too much, but the observed spectra is in black. And a cloudy model that does a decent job fitting it is shown in red. A cloudless model, like you're going to be doing today, is shown in blue. And you can see the cloudless model doesn't work at all. But when you put in clouds, it works fairly well. And so we know there has to be clouds there. A little bit cooler though, here's an example of 2-mass 0559. Data is in black, model is in blue, and this is now cloudless. If we try to model this object with clouds, they look like the red, which is nothing like what you've seen. So it may seem odd that I've spent a few minutes talking about clouds, which you're going to ignore today, but I think it's really important that you understand when we say these are cloudless models, we're looking more towards objects cooler than about 11 or 1200 Kelvin probably. which tends to be better fit by the cloud-free models. And to do this right in a full-up sense, a full-up analysis of data, you have to include clouds. So just be careful, I guess, is the point of those few slides. So in conclusion, the exercise today, what Natasha is going to be walking you through, is we're going to take those pre-computed pressure temperature profiles. We're going to use chemistry grids that our colleague Shannon Vischer has computed that tell you what the atmospheric abundances are at any given temperature and pressure. And so with the combination of the temperature pressure profiles, the chemistry grids, and then also opacities that you've downloaded, Picasso was able to compute spectra. And so we're sort of walking you through the process of producing these model spectra. And what you're going to be doing is varying the planet properties, varying the gravity, varying the temperature, and seeing how the spectra change. And then you can ask yourself, if you had real data, what would you be able to see? Could you see a small change in gravity, or does it have to be very big? And just try to build up some intuition. So don't be afraid to change parameters and move around and look at what happens. And so that's the summary. I do want to give a plug to all of you, especially if you're an undergraduate. Please consider applying to LPO for graduate school. We do lots of science on exoplanets and origins. And if you're a current grad student, please consider us for your prize postdoc packages, which I know you'll be putting together, including for 51 Peg B. So with that advertisement aside, we'd love to hear from you. And I'm going to hand this. Why don't I hand this over to Natasha, and then we'll take questions at the end.
Sounds good, Mark.
Okay, let's stop sharing.
Yeah, we only have a couple questions so far, so go to it, folks, and start typing them in. Natasha.
So do we have issues with screen advancement for me?
I see it advancing.
Yeah, you're good.
Okay, great. Awesome. Welcome, everyone. We're excited to be doing this hands-on session with everyone. And we have some great leaders as well who have been answering your questions in the Python channel and in the hands-on channel. And so I'd like to thank all of those folks as well listed down here. And they're going to be with you in the breakout sessions. And so you'll get to know them, and I'll have some logistical things towards the end of this. So in this follow-up, Mark gave a great intro overview of young planet spectroscopy, and I'm just going to be going into a little bit more detail in terms of the nuts and bolts of these hands-on sessions. I'm not going to fully walk through the notebooks, as I hope that you all will do that in your specific breakout sessions with your leaders. But I just wanted to give you more of an overview of sort of all of these ingredients that are going into the specifically Picasso here. But I want to sort of highlight the fact that once you really understand sort of the mechanism for producing, as in this case, we're focused on thermal emission of young planets, you'll all of a sudden have sort of the tools to start computing different kinds of spectra for different kinds of exoplanets. And so the skills that you're going to be learning here in terms of how to dissect planetary atmospheres, that those concepts that Mark was talking about how clouds affect spectroscopy are really applicable to, not identically, but very similar to other areas of exoplanet science, including transit spectroscopy and also reflected light spectroscopy. And so with that, as some of you are complete novices coming into doing spectroscopy modeling. Some people have a little bit more intuition for the spectroscopy modeling and are learning a little bit more about the planet formation side. And so I just want to, regardless of where you are, start out here all on the same footing. Theoretical modeling is comprised of these 5 main modules, pretty much across the board for any single code that you'll ever really use. There's the opacity component, the climate inputs, the chemistry inputs, the cloud, and then the spectroscopy, the radiative transfer component. So this opacity component is this pesky 6 gig file that everyone had to download and point to and create an environment variable, which I know everyone hates doing. So I apologize. But this is really going to be a component of any radiative transfer code that you use. So all spectroscopic codes, especially ones used for exoplanet science, use some form of either cross sections, or if they're line by line codes, they use sort of the sort of experimental or theoretically derived line lists that you can see here at the bottom of the screen. So these opacities are computed from, you can get more information on the ExoMol website or the HyTran website. The ExoMol group is sort of, has a bunch of infrastructure for computing sort of theoretically derived line intensities in transitions. And then the HyTran group is very good at aggregating lots of different kinds of data, bringing in experimental work and theoretical work to create these line lists. Once you have the line list, you can all in atmospheres, these lines are broadened by pressure sources or thermal sources, and by combining those two things, we can get out we compute what's called these cross sections, which is basically the effective absorbing area of your molecule, which tells you how each individual molecule is going to absorb light, which is, as you imagine, very important for computing these types of models. If you're interested in this component and how we actually get this file, because I know you all have just downloaded this and are using it at face value, Ahsan Gharib-Nezad just published a great paper on computing tons of opacities, which you can check out. And if you are going into grad school, a great course to take to understand some of this is aquatic chemistry, which is usually offered in a chemistry department, would also be incredibly useful. Now, these cross sections are computed on what's called line by line. So they're computed on grids of pressure and temperature, often thousands of grid points. And so each molecule is, for a single molecule, one cross section bundle is usually around 16 gigs. And so you might be thinking, well, I was given a 6 gigabyte file that had 10 or so molecules. So what happened from those original calculations to what I've provided you? And so what we've done in order to make the data transfer manageable is to resample this. And so you have received a resampled cross-section file at an R of 10,000. And the reason I emphasize this is it does have implications for your modeling. If you are using resampled cross-sections, it means that you have to rebin your final spectra down to 100 times lower resolution. And so as you're going through these tutorial notebooks, you're going to see this Picasso mean regrid down to R of 100 for every single step. And you might be tempted to check out higher resolutions. And I am telling everyone now that you probably shouldn't do this just for these tutorial examples because of this limitation in the file that I've provided. But I will say, if you are interested in going to higher resolution, contact us and we can provide you with a better suited file for your science. Okay, so that's the opacity stuff, and I'm going to skip through some of this, but I'll just say that this opacity, the reason why I'm harping on this is it is a really huge aspect of these models that you're going to be creating. And so if you have additional questions about whether this opacity file that you now have is suitable for the specific science problem that you're working on or interested in, definitely contact us, or you can also reach out to the line list teams directly. The ExoMol team and the HyTran team are always really good about answering questions. Okay, so in addition to the opacity, we also have to provide a pressure temperature profile, which Mark gave a great intro on. Just as Mark was describing, you'll notice that the Picasso function that you'll be using is called Sonora. And so these are a database of climate models, and Picasso is not computing these climate models from first principles. We're actually just interpolating from a grid based on a given gravity and effective temperature. And so all Picasso is doing at this step is going to the Sonora grid database, which you downloaded, and grabbing the most suitable PT profile for you. So once we have the pressure temperature profile, the next step is to actually set the chemistry. This is kind of done behind the scenes, and so you might not notice it directly when you're going through your modeling process. It's actually embedded within the Sonora function, because the chemistry portion we're assuming we have sort of solar metallicity and solar carbon oxygen ratios. And so that's sort of an aspect that we've sort of put behind the scenes just in these modules to make it a little bit simpler for you all. But you can actually go and check out all of the chemistry files that we have. The grids are both available on Zenodo, I think posted by Mark. You can check out Shannon Vischer's papers, which describe the chemistry calculations. And then you can see on GitHub what the file looks like. You'll see it's similarly computed on a grid of pressure and temperatures. This grid goes from 75 Kelvin all the way to 6,000 Kelvin at various different pressures. And so given these grids, we can take our pressure temperature profile, interpolate on the all of the chemistry that you were given, and you'll get out this nice abundance profile that you're going to be playing around with. And this is directly taken from that from the notebook that you'll be playing around with today. And you'll see sort of a load of molecules, their mixing ratio, which is a word that just means abundance or molecular abundance as a function of pressure. And so this is all done behind the scenes, but all of the modules can be found in sort of that Sonora function if you're interested in checking them out. So the next step is the cloud step, and as Mark already alluded to, we're in the first two notebooks, which are the main notebooks of the hands-on session. We are ignoring clouds completely. We have included an additional notebook that is included on the Picasso documentation page that has a whole breakdown of cloud modeling with Virga, which is an additional Python package. Also created by Mark and I and our postdoc Kiva Rooney. And the Virga will give you, given pressure temperature profile, in addition to some other cloud inputs, which this notebook briefly touches on, it gives you sort of an optical depth profile and scattering properties of the cloud itself. But I won't spend too much time talking about this because the main component of the workshops will be this last bit right here, which is the spectroscopy component, which is really where Picasso comes into play. And so Picasso is really ingesting all of these different inputs, the chemical model inputs, the climate model inputs, and the cloud inputs. And then given your specific observing geometry, whether it be transmission, emission, or reflected light, it will go and compute you a spectrum. And so this spectrum is effectively what you, the observer, are seeing, depending on what geometry you describe. And all of these different geometries, though we're not focused on them, kind of give you different information. Transmission spectroscopy is sensitive to high altitude abundances, high altitude temperatures, and just cloud extinction. Emission and reflected light are really sensitive to scattering properties. Emission is, more sensitive to the temperature pressure profile, as you'll see in our tutorial. And both emission and reflected light are also very sensitive to the abundances or the mixing ratios of the different molecules. And so this is another component of the tutorial. You'll see whenever you go to compute a spectrum, there's this little addendum in the spectrum function that says calculation equals thermal, and that's how you get out your thermal emission spectrum. So I just wanted to put in a plug here that Picasso is not the only radiative transfer code out there. And so if you've hated working with it so far, there are many others which you can choose from. They all do, the biggest thing you want to watch out for is just what geometries they compute. Some codes are specifically focused on transmission versus emission. And so make sure you just read whatever code's documentation to make sure that it's right for the problem that you want to work on. And then also you'll have to do some digging into what they use for their opacities as well to kind of understand, again, if the opacities that those authors have computed is right for the science problem that you have at hand. And just to say that this is not even close to an exhaustive list, there are a lot of resources out there, and so you just kind of have to dig around and see what's best for you. Okay, so hopefully you all are relatively familiar with the Picasso documentation page at this point. There are several tutorials. If you are specifically struggling with one component, I urge you to go to the documentation part. It's all searchable, so you can sort of search for the thing that you're interested in, whether it be clouds or chemistry or what have you, and check out some of the tutorials related to those aspects. The other thing I wanted to say is one thing that we're really not talking about in this tutorial is the specific radiative transfer methodology within Picasso. We're really focused on how these different input properties affect spectra, but we're not going to be focused on sort of the mathematics or the physics that goes into computing the spectra. If you are interested in this on your own time, there is this this clickable here link that takes you to the Picasso derivation page. We've created this interactive radiative transfer page that sort of takes you through all the different sort of assumptions and approximations that we make within the Picasso code. It'll sort of run you through, you know, what these different functions mean, the phase functions and all of that stuff, and all of the equations in this tutorial is sort of linked back to the GitHub page, so you can sort of follow along the derivations along with the code and sort of understand how all of that works. And so if you're really interested in that component, I encourage you to go check that out. Okay, so with that, I will just give a brief overview of sort of the goals of our hands-on session. First, we just want you to build an intuition for spectroscopy. This is, you know, become familiar with the evolution tracks that Mark covered, understand the modules and the inputs that are needed to create sort of planet atmospheres or models of spectra. And then the big one is really to understand how to dissect a planetary spectrum. This is going to be probably the biggest thing that you can take away from this hands-on session. And it is not enough to just be able to plop, you know, to create a spectrum. That doesn't really help you a lot, especially when you go to compare your models to data. Oftentimes what happens is you create this really nice model and then you plot it up against data and you'll see, you know, that you really don't get it right at all. And if you have an intuition for how to dissect planetary spectra and really understand the components that are going into creating the shape, the molecular structure of your spectra, you can start to understand what has gone wrong. Maybe your climate profile that you've input is incorrect. Maybe your abundances are wrong. Maybe you're missing a molecule, or maybe you've neglected the effect of clouds. And if you don't understand how clouds affect spectra, then it's really hard to understand and to really diagnose, you know, oh, maybe I should add a cloud model. And so as you're going through these modules, really, you know, try and make sure that you have an understanding for that. And as Mark said, one thing you can do to really gain that understanding is go back and fiddle with parameters and check out the output and go through the module again to make sure that you kind of understand exactly why the input that you made had the effect that it had. The next component will just be to understand the most current set of planet detections, which you've had a lot of great talks on, but now you're going to be plotting them up against these evolution tracks to really kind of start to dissect them and really understand what degeneracies exist in trying to determine the formation history of these different planets. Now, lastly, we do have this deep dive into the chemistry and clouds, which is sort of a bonus. And so this, you won't necessarily be doing this. This is notebooks 3 and 4. You won't necessarily be doing this in your specific hands-on sessions unless you've completely exhausted the first 2 modules. But if you're interested in doing this on your own or finding a buddy within the Sagan Summer School that's also interested in going through it, you're basically going to learn sort of what's happening as your atmosphere is cooling down. So how does chemistry change as a function of effective temperature? How does this affect the observable spectra? And most importantly, you're going to walk away with an understanding of what molecules are just most important to planetary spectroscopy at different temperatures. And then in the cloud module, it's going to be very similar, but just focused instead on chemistry, on clouds. And so what is the dominant cloud species that you expect at different temperatures? We'll give you a really brief understanding of sort of the additional cloud parameters that you need to go into modeling. And then really fold in this whole idea of diagnosing spectra, but with the addition of clouds. Lastly, just two more things following the, I've been following sort of the issues that people have had with the code itself. It looks like lots of people have issues with environment variables. So just in the last, within the last few days, I created an entire new section in the installation on creating environment variables. I've added 3 different ways to create environment variables. So if you're having issues with that, I would go check that out and try different ways to set those. And if you're still having issues, you can of course direct your questions to Python help channel, and hopefully someone will help you out. Here is a list of your fearless leaders. Just a few ground rules going forward. If possible during the hands-on sessions, and I'm sure you did this beforehand, so I'm probably just reiterating here, but do turn on your video. It really encourages participation, and I think you'll be more engaged. The more engaged you are, the more you'll learn, and it'll really help the leaders of each of the hands-on sessions. And then, of course, everyone's learning together. I know that from talking to people during the breakfast this morning, everyone's at different levels, whether it be undergrad, grad, or postdoc. So this is a judgment-free zone. Be respectful. Everyone's going to be learning together. And so hopefully everyone has a great time. Remember your meeting room number so that the next day, so tomorrow, you're going to be going to the same exact room. So hopefully you can build on sort of the discussion that you're starting today regarding the notebooks. And then Mark and I will be in the main room starting at 12:15 to answer more specific questions that you have. And then lastly, continue writing in questions Python help for sort of Python related questions. Try not to ask your leaders of the workshops those Python questions because it might derail some of the more science-based discussion questions there. And with that, I'll stop and we can take some questions.
Okay, thanks, Natasha. Let me correct an omission. In the rush to get started, I didn't introduce Natasha. She's a research scientist at NASA Ames in Mountain View, California, and she's also the leader of the largest community-based transit spectroscopy project selected for James Webb Space Telescope. So she's going to be very busy next year with a lot of cool stuff. All right, so we only have a few questions posted here. I think maybe people took seriously your comment that they should do it in the sessions where they can talk directly. But one question was, can Picasso be used for brown dwarf atmospheres?
Yep. So there is a notebook. So if you search in the Picasso documentation, there's a whole notebook dedicated to brown dwarfs. Actually, the process though for modeling young planets is very similar to brown dwarfs. The only difference is that you have to add a little tiny function that says no star. And so you'll just nix that. You'll swap out the star input function for the no star one, and that's pretty much it.
Okay, thanks.
And Natasha, I was going to answer a question. I think I deleted it. Was, can Picasso be used for retrievals? Do you want to take that?
Yeah. So yes, it can. So Picasso is the biggest thing when considering a code to use retrievals is how fast it is. And we have used, so Sagni Mukherjee has a great paper on using Picasso with retrievals. And so if you happen to end up in his session lead, you can ask him questions about it. And we are in the process of putting more of it. We don't have a great notebook tutorial on it. But you can sort of wrap your favorite, either Dynasty or MC or your favorite sampler and do retrievals with Picasso.
Okay, we have a question as to whether the mixing ratio is really an independent parameter in these models, or is it influenced by other atmosphere parameters?
So the mixing ratio is influenced by currently the way that the model setup is run in your in the tutorial is that the mixing ratios are determined from the pressure temperature profile, and that's the only thing that is affecting them. So if you go and look at those Shannon grids, you'll see that they're a function of pressure and temperature, and those are the only two parameters that are changing on that grid. And so one thing that the person asking the question is might be thinking of as a parameter like mixing, which is often thought of in chemical models, and so that will not be considered in your tutorials.
But does that mean, like, for example, you have condensation happening and changing the amount of a certain molecule in the gas phase? Is that happening in models?
So Mark can jump in here if he has a better answer, but I think that Shannon considers that stuff when he computes just his chemistry on his pressure temperature grid. But Picasso won't post-process any sort of other, depletion of abundances unless you hard code that in yourself.
But the grids condense. So if you're to the left of a condensation curve from Shannon's grids, it properly has removed the species that have condensed. What we don't have in what's being presented today is disequilibrium chemistry or mixing through condensation or past the equilibrium point. So these are all for what's known as pure rain out equilibrium.
Okay, well, another question that's come up is in terms of fitting model spectra to data, they're asking about how reliable are the parameters that are retrieved, and in particular, does the physics of the models get adjusted as part of the fitting process? Do you say this sort of treatment of a particular process, see how well that fits, and maybe adjust the treatment of that physical process to see if that makes the fit any better?
Yeah, that's a great question. So as you can see sort of in the hierarchy of even just the discussion that we're having right now, the addition of mixing, the addition of clouds, when you're setting up your retrieval problem, and the biggest thing that you really need to consider is what complexity, what are the parameters that you're fitting for? A lot of times that comes down to how many free parameters are you giving to a certain input, and those 5 inputs that I talked about. How many free parameters are you assigning to describe your pressure temperature profile? How many free parameters are you describing your cloud model with? And so when you're setting up your retrieval problem, a good method is to start with something simplistic and start with a simple model and expand it based on how you're based on the parameters that you do retrieve. And in the Mukherjee reflected light paper, we do this with cloud models. So we choose, sort of different, we increase the complexity of the cloud model to see how that affects the retrieved abundances. And it does. A lot of times you'll see huge differences in abundances. Eileen Gonzalez has another great paper that on brown dwarfs, where she did a very similar thing, retrieval exercise, where changing the different cloud models, retrieving abundances, and again, you see different answers based on your setup. And so it's super important to sort of don't do one retrieval and assume that you've gotten the correct answers. It's really important to sort of play around and see how, what setups are giving different answers.
One of the questions that's just come up maybe can be addressed in the following way, is that when we talk about retrieval just now, that's not something that the exercise today and tomorrow is going to be taking folks through. You're just going in the forward direction, calculating what the models look like. And retrieval is a whole other problem for folks with data.
That's true. And I will put in a plug. The early release science team they don't have a hands-on session this week, but the following Thursdays, every Thursday, the early release science team is having tutorials, and there is one specifically dedicated to retrievals. And so you can go to that hands-on session and learn sort of how to set up a retrieval problem if you're interested. Even if the retrieval problem is focused on transiting exoplanets, you'll be able to apply it to sort of young planet spectroscopy as well.
Yeah, so she's referring to another JWST science team whose data will all be immediately available as soon as the telescope is commissioned and ready for action. that's going to happen a little bit before Natasha's large program. And they're doing a lot of treatment for the community to get them all ready to work with that data through their own process like this workshop. Okay, well, we don't really have a whole bunch more questions. I think there will be many more in the individual sessions. We have questions about errors people are encountering, but I don't think we want to go through that in this forum. So maybe Natasha or Mark, do you want to make any concluding comments?
Just enjoy yourself and try to build intuition is the biggest thing that you can do. As Natasha said, it's just trying things and seeing what matters and what doesn't matter, and how things change, and then you can carry that with you.
Okay, well, thank you both very much. You attendees are lucky to have these two world experts in this area working with you today, so please take advantage.